So we have two irrotational vortex. The first one has a positive circulation gamma, and the second one has a negative circulation minus gamma. Now I can show you what the velocity field looks like. It looks like this. So the arrows represent again the velocity vector. So here you have one irrotational vortex with a positive circulation gamma, and here you have a negative irrotational vortex with the circulation negative gamma. Now it turns out, and we'll discuss that in more details in the coming weeks, it turns out that for irrotational vortex you can deduce the velocity field simply by adding the velocity fields due to both irrotational vortices. So it's actually quite easy to compute the velocity field. You simply have to take the velocity field which is created by one vortex, and you just add it to the velocity field created by the other vortex. That's not a trivial thing because the Navier-Stokes equations are nonlinear, but for irrotational flows, you can do that. We'll discuss that next week. Regardless, this is the velocity field, right? But the question is, what happens to those two vortices? And for that, we have to remember what this represents. Yeah? So this represents the material derivative of omega. So this represents really the transport, the advective transport of omega. Remember that the material derivative represents the time changes as you follow a material element. So those are the changes in time, or the variations, variations. This tells you how omega varies as you follow a material element, and therefore this equation simply says that the vorticity doesn't vary when you follow a material element. So in other terms, the vorticity is simply advected. So where do we have vorticity here? Where when we have irrotational vortex, we've discussed that we only have vorticity at the core of the vortex. So at this single point, we have a delta of vorticity. And at this point here, minus x naught y, we also have a delta of vorticity. And so that delta of vorticity, the vorticity which is concentrated here, is simply going to be advected with the velocity field. Now the question is, what is the velocity field at this point? It is simply the velocity field induced by the other vortex. So this vortex here creates a velocity field, which turns in this direction. It decays in 1 over r. So here, the velocity induced by, let me give them names. Let me call this one vortex 1 and this one here vortex 2. So if we think about the velocity induced by vortex 1 at the position here of vortex 2, it will be a velocity which is in the circumferential direction. So it will be in this direction. And the magnitude of this velocity will be, well, let's start about this. So what is the velocity, the flow velocity induced by the vortex 1 at the point x naught y? Now what is it? Well, in the u direction, in the x direction, it is equal to 0. We only have a non-zero component in the v direction, and it is negative gamma divided by 2 pi times the distance from this point to the core of the vortex. So this distance here is 2x naught times 2x naught. So it's really minus gamma times 4 pi x naught. This is the flow velocity field, the velocity of the flow at this point, and the vorticity is advected at this velocity. So this simply means that vortex 2 will move down with the velocity v equals minus gamma divided by 4 pi x naught. That's what's going to happen to vortex 2. Now what happens to vortex 1? Well, vortex 1 is going to be likewise advected with the velocity induced by vortex 2. So the flow velocity induced by the vortex 2 at the point minus x naught y, what is it? So we're thinking now about the velocity induced by this vortex, so by vortex 2, but at that point, now we simply have to look at the direction of the circulation. So the flow induced by 2 is going to move in this direction. So at 1 it's going to be in this direction here, in the circumferential direction. And again, it will be equal to, so u is going to be equal to 0 also. And v, the velocity in the y direction, is going to be equal, because it's turning in the anti-clockwise, counterclockwise direction, it will be equal to here minus gamma divided by 2 pi times the same distance, which is 2x naught. So it will be equal to minus gamma divided by 4 pi x naught. So essentially what will happen to this pair of vortex, each vortex is going to be advected by the velocity induced by the other vortex, and actually both will move downwards. So they move in the negative y direction with the same velocity. So the pair is just going to move in parallel in the downwards direction. So this is essentially the advection of vorticity if we neglect diffusion. Now, if we didn't neglect diffusion, then what we would have is that at the same time that those two vectors, those two vortices move downwards, pushed by the other vector, the core, the vorticity which is in the core, would also diffuse radially. So this is essentially what would happen if we included diffusion as well. Okay, so here we finish our discussion on the vorticity equation. We explain what it means for vorticity to be advected and for vorticity to diffuse. And now in this discussion on vortex dynamics, we reach the last point, which is the Kelvin circulation theorem. So we will derive the Kelvin circulation theorem. So let me just write down Kelvin circulation theorem. So we will derive the theorem. It's important you are able to roughly understand and follow the derivation, but this is not a derivation which I would ask you to reproduce in an exam. You just need to understand the result and where it comes from. So for the Kelvin circulation theorem, we assume that the flow is inviscid. So there are a few assumptions. We assume the flow is inviscid, incompressible, that the external forces are conservative. That means essentially that the body force term F in Navier-Stokes equation derives from a potential. Conservative. That means that F is equals to minus the gradient of a force potential. And so in principle, you assume a barotropic flow, which means that the density is only a function of the pressure. Right? So density only function of pressure. So this is more general, but here I'm simply going to assume that the density is a constant, so that the fluid is incompressible. So here we assume rho constant, which is a stronger assumption that really is necessary. The derivation will be the same. There's just a little thing which will be a bit more complex for barotropic flows. So it doesn't change much. Well, I'm just assuming that the fluid is incompressible. So we have an incompressible fluid. Okay, now let me first state Kelvin's circulation theorem. So let's assume that we have a closed contour C. But now it's not just any contour. This closed contour C is a material contour. That means that the contour is moving with the flow. So this is here, let me call CT is a material contour, which means that the contour is moving with the flow field. In other words, that means that this point here along the contour, my contour is changing, and this point along the contour is moving at any time t at the flow velocity, at ut. Okay, so Kelvin's circulation theorem is the following. And that is that the circulation around a material contour, so around a contour moving with the flow, around a contour moving with the flow, and that is of course assuming the flow is inviscid, the flow is incompressible, and the external forces are conservative. The fluid is incompressible and the external forces are conservative. In that case, the circulation around a material contour is constant. This here is the Kelvin circulation theorem. In mathematical terms, you would just write it as d over dt of gamma, where this gamma here is equal to the circulation, so the line integral of the velocity field, but along a material contour. So this contour is a function of t. So d over dt of gamma is equal to 0. Okay, that here is the circulation, Kelvin's circulation theorem. And we'll see that it will help us understand vortex shedding, starting vortices, and so on. So here I'm going to quickly derive this result so you have an idea where it comes from. And so we'll start from the time derivative of the circulation. Again, remember this is a circulation around a material contour. So this is equal to d over dt of this integral along a closed contour u dot dl. Now again, we have this thing of having a time derivative of an integral which is a function of time. So what we want to do is to put this time derivative inside of the control, inside of the integral. Now when we do that, we have the same, we've discussed that, then we cannot just take the partial derivative, and in fact in that case what we simply have to do is to take the material derivative. So if we're thinking about the time changes of this material contour, because this integral now is on a material contour, well then if we want to put the time derivative inside of the integral, we just have to take the material derivative. So this is equal to integral along our closed material contour of the material derivative of u dot dl. And now we can simply take the product, the derivative of a product. So we have the integral along the closed contour of the material derivative of the velocity field dot dl plus u dot the material derivative of our differential element of displacement along the contour. Now remember, this contour here, this contour is moving, so my dl is also a function of time. Later on, this contour will have translated somewhere here, will have moved and deformed, and therefore the dl will have moved as well. So this dl is not constant in time. So I have two terms in this integral, 1 and 2. We'll just look at them separately. So let's start with 1. So 1 is the integral along my material contour of the material derivative of u, the material derivative of the velocity field dot dl. Now we're just going to use the momentum equation of Navier-Stokes equation to express du dt. Right? So du dt is the term which is on the left-hand side. So we just have to write that this is equal to 1 over rho times the du dt is on the left-hand side. So we have to take 1 over rho times the right-hand side of Navier-Stokes equation. So this is minus grad p plus mu times the Laplacian of u minus our force potential dot dl. So first of all, we assume the flow is inviscid, so we can neglect, this term is negligible. And then we are left with integral along a closed contour of a gradient. So because of the fundamental theorem of calculus, we know that these are going to be equal to 0. Now, I'm assuming that rho is only a function of, is actually a constant. Let me make that easier. I'm going to assume rho, the fluid is incompressible, so rho is a constant. I can take it outside of the integral with the minus sign. Integral along a closed contour of gradient of p plus gradient of phi, right, dot dl. And by definition, I should say, because of the fundamental theorem of calculus, this is equal to 0 because we are integrating along a closed contour. So if the contour wasn't open, just to remind you what the fundamental theorem of calculus is, if I was integrating between any point A and B the gradient of P dot dl, that would be equal to the pressure at B minus the pressure at A. But because we are integrating along a closed contour, my point B and my point A are the same. So this is equal to 0. Now, the second term is the integral. So the integral along a closed contour of u dot the material derivative of dl. So this is u dot the material derivative of dl. And now it's not easy to see what this term here represents. So let's make that a little bit clearer. So let's zoom in on a little part of our contour. Now, contour, where's my contour? It's up here. It's a bit too small. So let me just zoom in on the contour. So let's say this is here my contour. Okay, and I'm going to zoom in on that little section here of my contour. So this is the contour, and here I have dl. So what is dl? Really, it is, in a way, the difference between the position vector at an arc length s. So this point is at position xs, and this point here is at the position xs plus a length dl. Right? It's really this vector dl is the difference between those two position vectors here. So this is equal to dt, so the material derivative of x at s plus dl minus the position vector at x. But what is the material derivative of the position vector on a contour which is moving with the flow? Now, if you think long about this, it's an intricate definition. The definition for vector, but the material derivative of a point, of this point here, and this point here is actually following the flow, is simply the velocity. So this is the velocity field at the velocity vector, at s plus dl, and d, the material derivative of x of s, is the velocity at point S. So this is this is what this is, right? So this is equal to the integral along the closed contour, which depends on t, of u dot this here we can call a du. It's the change, the difference in velocity between this point here and that point here. So we can call it du. Du along the contour. And therefore we can integrate, right? This is an exact differential. So this is equal to u dot du. So it's the exact differential of 1/2 d of u dot u. So we can integrate that because it's an exact differential, so it's really equal to 1/2 of u dot u, let me say at the start point, of my contour, so at any point around my contour, minus 1/2 u dot u at the end point of my contour. But of course, if my contour is closed, the start point equals the end point along a closed contour. Along closed contour. And therefore, this is equal to 0. So therefore, this integral of u material derivative of the differential element of displacement along the contour is equal to 0, and we are left with the Kelvin circulation theorem, that the derivative of the circulation along a material contour is equal to 0, or the circulation around a material contour does not change. Okay, so try to keep this result in your mind, because we'll discuss that again. We'll get back to that later on when we discuss certain applications of vortices, especially in aerodynamics. Okay, so now we're done with vortex dynamics. So I'm going to change page, and we're going to move on to our next topic, which will focus on flows and flow representations and ways to deduce the flow velocity field and the pressure field when the effect of viscosity is negligible. So we will go from, and in particular we will focus on irrotational flows, so not just inviscid flows, but what are called ideal flows. So we'll go from inviscid flows to ideal flows. And this is part of Kundu. The reading is in Kundu on chapter 7. So let's start, because we're going to go back to Navier-Stokes equation and the Euler's equation. So let's start with a summary of the governing equations in advanced fluid dynamics so far. So summary of governing equations in IFD. So here is our the general set of partial differential equations, PDEs, that govern flow. The mass conservation for incompressible flows we can write as the divergence of u equals to 0. This is the continuity equation, or the mass conservation equation. It derives, I should say, from the mass conservation. And the momentum equation, which is rho times partial u partial t plus u grad u, is equal to the pressure term plus the viscous term minus, and I'm going to write again the forces in terms of conservative body forces. So we assume that the body force are conservative. Conservative body forces. Okay, this here is the momentum equation. So these are the general equations for incompressible, I should write here, one, incompressible flows. Now, when we assume that on top of that the flow is inviscid, that means that the viscosity term is negligible. So here we have two incompressible and inviscid flows. What we have is then that the continuity equation doesn't change, but we now have Euler's equations. We neglect the viscous term, and we end up having this equation here. So those are Euler's equations. Now, when we derived Bernoulli's equation, we rewrote this term here, and you can rewrite it as 1/2 of the gradient of u dot u minus u cross product w omega. So this is one way of writing it. Let me call that 2, and then there is 2 prime, which we have already done. But you can just write that the continuity equation doesn't change, but you rewrite the momentum equation as rho partial u over partial t plus the gradient of a scalar quantity, which is p plus 1/2 rho times the norm of u squared plus the force potential is equal to u cross product with the vorticity. And what we had discussed is that if you assume that the flow is steady, therefore this term here is equal to 0, and if you follow a streamline, in which case this here is equal to 0, then that quantity, p plus 1/2 of rho u squared plus phi, is a constant. And so this is Bernoulli equation in the weaker form, where you can only apply it for steady flows along a streamline. So what we'll discuss now is irrotational flows, and we'll see that when the flow is irrotational, so it's an additional assumption, the flow is, as a consequence, inviscid, and we'll find a stronger form for the Bernoulli equation. So let's move to assume on top of that irrotational flows. So what happens when the flow is irrotational and it is still incompressible? Compressible flows. So let me just start with a general remark, and I'll just mention, because at some point things will become confusing. So we discussed inviscid flows before we started discussing irrotationality. So the two are linked. In a way, there is a relation between the two, but they're not the same. So I just want you really to remember that an inviscid flows does not always imply irrotational flows. So if you have an inviscid flow, you could have an inviscid flow that is not irrotational. However, we'll see that if the flow is irrotational, then necessarily it is inviscid. Irrotational and incompressible, I should say. So that's the first thing I want you to remember. And then the second one is just, let's remember what it means to be irrotational. A flow is irrotational simply when it is curl-free. So when the curl of u is equal to 0, or another way of saying that is that the vorticity vector is equal to 0. Now let's look at a direct consequence of irrotationality. So what is the direct consequence of having an irrotational flow? So here we are going to use an identity which you could find again in the handout. So it's just a vector analysis identity which you're not expected to remember. But let's write that we have the vorticity vector which is equal to 0, and let's take the curl of the vorticity vector. Let's take the curl of this whole thing. I'm taking the curl of that here. So the curl of the vorticity is equal to the curl of the velocity, and there is a mathematical formula for the curl of the curl, which you can find in your handout. And the curl of u is equal to the gradient of the divergence of u minus the Laplacian of u. Now let's look at this. Since omega for irrotational flows, omega is equal to 0. So if omega is equal to 0, the curl will certainly be equal to 0. Here, omega equals to 0. So if you take any differential operator of something which is equal to 0, you'll just get 0. So the left-hand side here is equal to 0. And on the right-hand side, we have the gradient of the divergence of u. But if the flow is incompressible, then the divergence of u is equal to 0. Divergence of u is equal to 0 because we assume that the flow is incompressible. So here we're left with just the Laplacian of u is equal to 0. So in particular, if the Laplacian of u is equal to 0, then the viscous term, which is mu times the Laplacian of u, is negligible. It's equal to 0. Yeah? So the direct consequence of that is if the flow is incompressible, if the flow is irrotational, and the flow is incompressible, and for an incompressible fluid or for an incompressible flow, we need both, then the viscous term mu times the Laplacian of u is equal to 0. Note that you do not require that the fluid is inviscid. The Laplacian of u is equal to 0. The viscosity might not be 0. So we're not here neglecting the viscosity, but the flow, the kinematics of the flow, the velocity field, is such that there is no Laplacian, and that therefore the viscosity does not act, and there is no the viscous term in the Navier-Stokes equation drops out. So then mu Laplacian of u is equal to 0, and so that means that the viscous term in the Navier-Stokes equation is negligible. It is 0, I should say, even. Okay, and therefore, in that case, Navier-Stokes equation reduces to Euler's equation as well. Okay, so now let's see what to the Euler equation when the flow is irrotational. And what it will lead to is what is called the unsteady Bernoulli equation. And I actually see that it's been 40 minutes. So I'm going to stop here. We'll continue that. Next Tuesday, and I will let Koen answer questions that you may have. Note again that for Friday, it would be good for you to review your notes on control volume analysis, so that you have questions and that you are prepared to do the problems.